so much. So thanks for all the courageous ones that are still here at 9:30 on a very hot day. So I will try to close this today, the story, which is not closed, of course, but so this is probably the most important of the three lectures. So let me remind you, because it's already more than 2 days ago, you may have forgotten. So I was trying to explain the, so I'm talking about SGD, gradient descent optimization in very high dimension for usual, classical tasks of machine learning type things or high dimensional statistics. And I chose as a first example the example of Tensor PCA, which was not machine learning, which was just statistics. So if you remember the rank the one spike tensor PCA, you have one vector, one unit vector in high dimension that you don't know. And what you have access to is this unit vector to the power p, let's say 3. So in the tensor version of this, so you have access to a large cube size n by n by n in dimension 3 of numbers, and what it is, it's your power 3 of the vector plus a little bit of noise. Okay, that was the model we had. So I will of course rewrite it, but just in case you, what you have access to is this. Okay, so you have a sample. That's a kind of the very simple example to start with. So you have a sample of size m. This u is the unknown vector. And I assume that we knew one thing about it, that is, we knew that it was norm 1. And so this one is the unknown, that's the signal, that's the thing you want to find. Lambda will be called a signal to noise ratio, naturally, because of course, again, if you put lambda here, this would be 1 over lambda would be the variance of the noise. So 1 over lambda is the variance of the noise. Lambda is a signal to noise ratio. And the WIs are the noise. They are IID, tensors, and let's say Gaussian. So you have white noise on every coordinate of your tensor, and you try to recover U. That was the question we looked at. All right? From this sample. This identity, of course, is in this n to the cube dimension. And you try, remember what we did, you look at this, and the first thing you try is the maximum likelihood estimation. So, which is obvious because this thing is Gaussian, so computing the distribution of this is trivial, it's a Gaussian thing. The likelihood is easy to compute. The log likelihood is quadratic. So when you compute the likelihood of this, what you find, the function you have to minimize, if you take an empirical function, has exactly the shape that I said before. Let's say that it has the shape lambda x u to the p plus a spin glass. I forgot how I call these things. Okay, let me call them J. The J's are just the W's, essentially. And remember, so that would be the function you wanted to minimize. So I started my first lecture by looking at this function, where these guys are IID random. So a random homogeneous polynomial of degree p, which is also an isotropic Gaussian process and one of the very few. And and of course for physics, that the p-spin glass, okay, spherical spin glass, because I'm on the sphere here. And I told you then, so if you consider just this guy, which of course for statistics would be stupid, you're trying to estimate without a signal. This had two difficulties, remember, the two layers. One was topological. The topology of this function is extremely complicated on the sphere, even though the function is stupidly simple, it's just a polynomial. So this function has exponentially many local minima, exponentially many critical points of every index. Essentially, I gave you this structure and how this is related to the understanding of the Gibbs measure we have from spin glass theory. Okay, and also how it is this topological understanding gives you more than the Parisi picture. It gives you details on this phase, which is above the spin glass phase, which is called the shattering phase, which is in fact, so in the spin glass phase at low temperature, in the bottom of this landscape, you have this, all these wells, and the Gibbs measure is carried by a finite number of them. But when you climb above that, you have exponentially many of these wells, which are at higher temperature, which the Gibbs measure doesn't see, the replica doesn't see, but which the dynamics see, right? When you try to optimize and you start from a point at random, you come from high in energy, you go down, you meet the shattering phase, which will essentially stop you. And this shattering phase corresponds to what is called the dynamic transition, all right? So this topology and this is where the dynamics of optimization and the topology meet. That's when you try to understand the role of this high-level shattering phase as a blocker of the dynamics in some sense. And then there was a transition above that, which was the metastability transition, the one we call the BBM transition, the Barra-Burioni-Mézard transition. All right, that was just physics, and there was all this. And then at some point I said, you may add this. So remember the picture I drew of a sphere, and so we were adding, we were saying when you, again, and I told you how this picture was not the right one. You had the equator here, and how of course, most of the mass of the sphere is at the equator, as we know. But so if you start at a point at random, you start at the equator, and then you want to go there, okay? So then we started again with the topological picture. When you add a signal, there are different regimes, which I'll remind very briefly. When the signal, there is a regime where the signal exists, lambda is positive, but you cannot find it, whatever you do, okay? And in particular here, it's visible topologically in this picture because all the local minima, all the critical points are at the equator. Okay, so even though you have a signal, your maximum likelihood estimation will give you a point which is non-informative, which will give you a point at the equator, so it's completely useless. No correlation with the signal. Okay? In fact, there's a deeper theorem at the information theory level telling you that it's not the fault of the maximum likelihood method. Whatever you do, you will not find the signal. Okay, so there is an information theory threshold below which the distance between the distribution with the signal and without the signal goes to 0. Okay, so in particular for the maximum likelihood, all the critical points are here. Then there is a phase where you see a parallel of on this parallel here. On this latitude, you see critical points, not exponentially many. But the global minimum is still here, so these are useless. And then there's a level of signal-to-noise ratio where you have critical points there, and the global minimum is somewhere here. And then you even have another phase where if lambda increases even more, where you have what I called topological trivialization, which means that the number of critical points in this informative region becomes 1. Right? You have only one, and that's the global minimum or maximum that you want to find. Okay? Of course, be careful because topological trivialization doesn't mean that the landscape is becoming trivial. At the equator, you still always have, because at the equator, when you take if you take this thing to be close to 0, essentially you have a spin glass. So at the equator, the landscape is still extremely complicated. You always have exponentially many local minima. It's a big mess, okay? But still, it's topologically trivial in the informative region, all right? And then we went to dynamics, and I said, dynamics, how do they work? Essentially, you project, what you find is you look at the projection of your evolution of xt you take the evolution of xt by stochastic gradient descent. And if you look at its projection on V, oh, did I call it U? I'm sorry. On U, this thing, so the projection here, is what we will call a summary statistics. It summarizes everything for a very good reason. Your thing here, the population the population loss, which is the expectation of that, is just this. So it depends only on this variable. So the dynamics of this, which is a priori in very high dimension, xt is in very high dimension, this one-dimensional projection is essentially autonomous, right? Not really. There is a little remainder that you have to control, but this satisfies an ODE. And this, so this ODE, when you are in dimension 1, this thing, let's call it, I don't know, MT, when you start at time 0, this is roughly 0, right? Because you start at the equator. But the ODE you have here, the gradient flow that you get, is the gradient of this, okay? So basically your evolution is something like dmt over dt equals minus gradient of this thing, which is mt p to the p minus 1, right? Roughly, plus small terms that I just don't want to consider. So you see you have a very simple dynamical system in dimension 1, where you start at 0, and you follow this thing. But of course, when p is larger or equal to 3, which is in the case of a tensor, this is why we're taking tensors and not vectors then this thing, of course, not only does this gradient vanishes at 0, right? But its derivative also vanishes at 0. So this is a very flat thing. And then everybody can solve this equation, this ODE, that's calculus 1. And if you do, you will see that it takes time to exit the neighborhood of 0, right? That's why you need a lot of time to get away from 0. And remember, in our picture, for SGD, time was money, time was data. Each time step is one data point. So the more time you need, the more data you need, okay? Or equivalently, the more signal-to-noise ratio you need, right? Okay, so that was the picture in dimension 1, which started us in this thing. I'm sure you remembered everything, of course, but I thought maybe I should recall, right? It's an old teacher. So now let me go to, so that's nice, we can play with that, and then maybe I gave you, I don't remember now, if I had time to talk about other examples, I mentioned them, so the first step that happened in this theory, which I described a bit, was that at some point we realized that for the dynamical part, not for the topological part, we didn't need to know that this was a function we understood well, so we could get rid of physics of spin glasses, right? The only thing we needed was the projection, this object, right? So then we have, in 1D, there are plenty of models like that, right? I mentioned phase retrieval. Maybe you don't know that, but there are plenty. But I will now give you, so then the next step was, but this is dimension 1, so let's go to, it's possible maybe that we have projection in dimension 17. So that's what summary statistics and effective dynamics are. So let me I go back first to the analysis in high dimension and the notation, which I gave you in the very first lecture. So now P is an unknown probability distribution on an open set of RD. We have a loss function, which was this in our case, defined on V cross U, where U is the parameter space, where U is the data space and V is the parameter space. And the goal is to find the minimum of the population loss, phi of x, which is the expectation of L of xy. And of course, you have devised your statistical procedure here, your loss function, so that the minimum of this population loss is the true value of the parameter and to estimate P. So of course, we don't know the distribution P, so we cannot really compute this population loss that we want to minimize. It's an optimization problem with an function we need to minimize that we don't really know. So, and as I said, I will study the case of online SGD only, which is one variant. Online SGD is this. At time L minus 1, you're at a certain space position XL minus 1. You go to XL by just subtracting the gradient of the loss at the point where you are. Oops. Here, but given just one data point. And you have to specify here what this constant is, and it's crucial constant called the learning rate. And then, of course, in order to specify this thing, you have to say where you start. As I mentioned, of course, in SGD, you could do many different things. Instead of taking one function, one data point here, you could take a batch of data point, 25 data points, that's called a batch, and you take the average on the batch. Okay? And then you can choose the size of the batch. Here, this is the minimal size of the batch. That's why it's called online SGD. If you take the maximal size of the batch, which is all the data you have at every point, this is called the gradient descent for the empirical loss. Okay? But of course, this is the most economical. I mean, you just use one data point every time. Right? So in terms of compute, this is much less demanding than going through your whole sample at every step. So, all right, so the interest again, as I mentioned, it's to understand this evolution here, Excel, in the regime where the dimension of the parameter space is large, the dimension of the data space is large, but the size of the sample is not too large. Again, that's the important thing. We are not supposed to have an extraordinarily large amount of data, okay? If we did, if m really tends to infinity as fast as you want, as exponential of d, exponential p, whatever, then you would be like in the classical regime. And in the classical regime, we know when the dimensions are fixed and m goes to infinity, we know that online SGD converges to a very simple thing, which is the thing you want. This is why SGD was introduced. It converges to the gradient flow of the population loss. Right? So imagine that you are in finite dimension, you're doing optimization in the 50s. Then this thing, of course, you have the population loss. One thing one system you want to think about is to take the gradient flow of the population loss. This is supposed to go down. Except here it's much simpler than doing that, because first you don't know the population loss, you don't have to estimate it, you just take, at every step you take a data point. Right? So if you have the leisure to have a very long m, it will be the gradient flow of the population. That's what justifies using SGD. But here we are in a regime where m is not too large. We want to have this work with not that much data. Are we still in the regime where we see something like the gradient flow or not? Are we going down? Do we find the minimum? This type of question. All right? Are you with me? Okay, so let's move. So the first question, so now we are in this regime, and the first question, so we have this object here. The dimension d in which this evolution takes place is not fixed, going to infinity. And so the first question is, how do you state the theorem? Right? That's a math question, of course, but think of it. You have your system going, the dimension is very large. What is supposed to converge? Right? So one way, of course, in simpler things, I don't know, you do some mean field thing, which is simpler. Then you have, your system is exchangeable. So you have a natural object, which is to look at the empirical measure, right? This should converge. That's the trick of mean field, always. Here, what would converge? It's not clear, right? You have a path. Your SGD it's a path in a space which dimension increases. So how do you state something converges, right? So one way, of course, is to remember that in many cases, of course, so again, it's my usual two numbers. You have a space in dimension 10 to the 9. Okay, but in fact, it could be 10 to the 12 or 10 to the 14. If you wait long enough, Google will have gone to 10 to the 15. So what does converge? But in fact, of course, you don't want to follow this 10 to the 9 parameters. You don't care, right? So in most problems, you don't need to follow the full parameter along the path of the SGD. So we start with the idea that in fact you just need to follow a few of them. Okay, so you could say, and this is what we'll call summary statistics. But if you take a projection, okay, in my classical dimension 17, right? You think you have 17 things that you want to look at. There is no reason that this 17 projection in dimension 17 has an autonomous dynamics. Right? If you think of your system of SGD to be something like the gradient flow of your population loss. If you take the gradient flow of something and you project it in 17 dimension, it's not an ODE. Right? You take an ODE and you project it in lower dimension, you don't get an ODE, right? You all see that, right? Not sure. Okay. So in general, there is no reason for projections to be autonomous. So what we want, here we say we will call summary statistics low dimensional projection in dimension 17, such that their dynamics are, at least locally, almost autonomous. Right? And the next thing, of course, is that we want to choose them. I mean, it's easy to find that. Just project on 0, right? That's autonomous. That's stupid. So you want this projection to be informative, to tell you something about the performance of the system. Yes?
But you don't know in advance what this is.
Absolutely not. That's the perfect question for the end of this talk. So you don't know, of course. That's, if you knew, then you don't need to do all this, right? So you don't know how to project. What is the thing you want to follow, right? So for the moment, I will take just the beginning of this will be to look at when the structure exists. And then you have to understand, so in some cases, you have a guess on what you want to follow. But in many cases you don't, and so then you have to ask yourself the question, how do I find them? And then how do you find them? The answer to all this thing in statistics, the answer is always BBP. It's always the spectral, it's like PCA. It's always spectral, so we'll get to that, okay? So this, but if you can do that, then the question reduces to a finite dimensional dynamical system that I will call the effective dynamics. So think of this. You have a very high dimensional 10 to the 9 sphere. In this case, you knew what you want to follow, which is this correlation with the signal. Of course, you don't know where U is, right? But this thing satisfies an ODE. This ... means almost autonomous. You have some error terms. All right? So
actually, in physics, this is a very common
it's
thing to project, but in general, you know in advance what kind of parameters you would be interested in.
Yes, but in statistics, you don't know.
Except in the easy models, the one with which you invent these things, yes, you do. But then in harder models, you have to let the model does it on its own. And by the way, as you will see, the model doesn't know if the dimension is 17 or 92. And then maybe he will find something, the system will find something of dimension 4 and then dimension 6 and then go back to dimension 4 and then to go to all things can happen. And maybe we'll find a projection in dimension 6, but which is completely irrelevant. Right? So we'll see all that. Of course, the end, if you want to stop listening now, the end of the story is that if the signal to noise ratio is strong enough, and if you have a low dimensional structure, it will emerge and it will be good. That's, but the question is how strong should it be? So, of course, the idea that nothing works in dimension 10 to the 9, but only in dimension 17, it's Occam's razor, right? The principle of parsimony, which says that in Latin and that in English. Of course, when Occam was thinking about that, his 17 was 1, right? Because 1 was God, right? So, so you didn't have 17, you have 1. To explain the whole universe, what he was saying is to explain the whole universe, you need one parameter, one entity, and that's it. So since it's the simplest, that's the explanation. I'm not going into philosophy, I'm just having fun here. So we've seen plenty of examples, we've seen not plenty, but a few examples where these summary statistics exist and are in dimension 1. For instance, this one. But in general, as was just mentioned here, nobody tells us if these projections exist or how to find them. My principle here is that if something works, if your SGD works in a reasonably short time, that is reasonably short data, and the result is reasonable, it must be somewhere that there is a low-dimensional thing explaining everything.
So, Gérard, if the dimension of my data is really high, but the number of symmetries in that data is high as well, then the game is easier, right? So
no, if you go from n cubed to n squared, it's still very large. What you're saying is that if your group of symmetries is the same dimension, same order of magnitude, yeah, then of course it's easy. But then what would this find? Precisely the quotient group. That's exactly what you're... If you don't know the symmetry, this one would find the motion in the orbit, in the quotient group. Okay, so this is joint work with Reza Gheissari and Aukosh Jagganath, called high-dimensional limit theorem, blah, blah, blah. And you have a short version, if you don't want to have a long version in the machine learning thing, EURIPS, and you have a long version in the communication and pure and applied math, the Courant journal. So what I'll do in the coming half hour, I will introduce the formal definition of this projection thing, this summary statistics, then proceed to prove under some regularity thing, the dynamics are indeed autonomous, and we'll call this dynamics effective. Then but already I should mention that these dynamics, this effective dynamics in dimension 17, depend dramatically. They depend on where you start. So for instance here, warm versus cold. No, cold versus warm, right? If you start here, then of course your dynamics are very slow. If you start here, then this dynamics will be very fast. It will just zoom there, right? So depending on where you start, depending in which parameter regions in which you're developing the scaling limit and the scaling of the step size with the dimension. Careful, you could have, so this idea is you have this thing in dimension 10 to the 9 and you say here, in this region I can project in dimension 17. The projection could move with a point. It's not necessarily a subspace, right? But maybe here the projection is dimension 5, right? This is what I was saying with the number of spikes that come out. Okay, so this is, you have, and maybe you start here, maybe you start here, and then you come here. Maybe your number of the dimension moves along the trajectory. Right? You see suddenly some coordinates become frozen essentially. Right? So all that can happen. Okay, but the important thing here I will insist on is the step size, with how the step size, the delta, remember, scales with the dimension. That will be very important. Okay? So let's think, before saying anything, let's think of what should happen. Remember what the step size is, right? It's really the size of the step you do multiplied by the gradient of your loss. It should be clear that if you take this step size absolutely microscopic, very, very, very small, what you get is something like a gradient flow. But maybe you don't go very far. Now, if you take very big step size, maybe your system is unstable because you take a gradient here which is completely random depending on your data point, and then you take a very big step size with the next data point, this thing, why would that converge? Right? So there must be a balance between these two things, and this is what we'll see. And of course, what is the cool thing? That you will have a regime of step size where things work well and are simple, like the gradient flow, a regime of step size where things are very unstable and you'd better not touch that, and everything cool happens at the edge. Back to physics, it's the critical regime that is cool and interesting, which is called the edge of stability. We'll describe that. Okay. So in practice, as GD often exhibits, I tell you results of many examples that we've treated so that I don't have to show you all that, but you can remember what it does. So exhibit two types of phases in training: ballistic phases, where the summary statistics macroscopically change in value. It's like an ODE moving along the flow of something. And diffusive phases where they fluctuate microscopically. And you've seen that here. Take this example. If I start with a random point, I will start very near 0, and I start with a diffusive phase, right? This thing will essentially wander around because the gradient is not strong enough. You have noise that you could see like Brownian. And then once you move, once you reach a level above, once you reach the hemisphere, then you will move fast. This will be ballistic, right? So you start here, you start with diffusive, and then you do ballistic, okay? In other examples, it may be much more complicated. Here, this is simple because you have one critical region, right? One slow region. But now imagine you're in dimension 17, you could have plenty of slow region. And now, depending on where you start, so you could be lucky and start in a fast region. But you could be unlucky and start in a very slow region. Then it takes time to escape, and then maybe you have this complicated dynamical system. Where do you go next? And you could travel around all these attractors for a while before getting to the points where you want to be, which is near the maximum or minimum. Okay? So that's the story. So you have ballistic and diffusive phases. Diffusive when you're close to one of those critical regions, and ballistic when you move. So during training, the evolution can start with either, here it started with diffusive, and can even alternate multiple times between these phases. So, and you can develop scaling limit for all these phases. So in ballistic phases, the effective dynamics are given by ODEs, and the finite dimensional intuition, the one when data is very large, that the summary statistics evolve under the gradient flow of the population loss is essentially correct, provided the learning rate is sufficiently small in the dimension, right? So if you do small enough steps, you will be as if your dimension was not diverging. The theorem proved by Robbins and Monroe in 51 is essentially still valid. Okay? Your system is like the gradient flow of the population loss. But the edge of stability, when the learning rate follows a certain critical scaling, which called the edge of stability, which match scalings commonly used in the high dimensional statistics or machine learning literature, and of course this depends on the problem, then an additional correction terms appears. You don't have the gradient flow of the population loss. You have something else. And the phase portrait deviates significantly from that of the population gradient flow. So this, it took me an enormous time to understand why serious people in this world use SGD. What? Okay, it's one reason is simple. It's because you use only one data point. So it's kind of economical in terms of machine size that you have to use. But why that? And the real reason is hidden there. So let me say it in math or physics term. Whether you do gradient flow or gradient descent, or you take the empirical whatever, or of course as a physicist, a Langevin type of thing. This is what, of course, for instance, when I mention dynamics for spin glasses, of course you think Langevin, that's the natural thing. You follow the gradient, you add some noise. All these things are cool for physics because they are reversible. Right? These things are self-adjoint if you want. You can reverse the sense of time, the direction of time. They are reversible. And they are cool for mathematicians because they are reversible. Reversible is simpler by far to analyze. When you do SGD, it's not a priori reversible. And so what we say here is that when the step size is small enough, in the limit, it's like the gradient flow, it's the limit of something. There is no obstruction. But at the edge of stability, this extra term does something which is not of gradient type, right? And it could be very bad. In some cases, it is in fact very good. It helps. So in the microscopic neighborhood of the fixed points, like here, of course, the effective dynamics become diffusive and are given by stochastic differential equation with all sorts of possibly degenerate behaviors. Of course, remember when I say microscopic, here microscopic neighborhood of 0 here is in fact the equator on the sphere. So it's in fact, it's microscopic, but it carries all the mass, right, in the high dimensional setting. Okay, but in the projection, it's just a tiny thing. Okay. So when you are interested at what's going on in those critical regions, you can do rescaling. You can rescale time, and then you have new dynamical systems appearing. I won't spend time here. Let me go back now with this vision. I didn't give you the exact statement of the theorems. Don't worry, I will. You will see a list of conditions for this thing to exist. Because remember, we have no, for the moment I say, under some abstract Bourbaki-like condition, then the projection is autonomous. Right? Then, of course, this is useful only if you have good examples and then a proof of the theorem. So I start with examples. Right? So let's start with what we know, matrix and tensor PCA. So the first example is is matrix PCA. So remember that's exactly what I wrote here, except that this K is P, and I forgot to put the tensor thing. So the loss is, of course, this. You can do it on the sphere as we did. Then, as we've seen, the one-dimensional effective dynamics here are exactly solvable. They are essentially this. I wrote them here. You can also do them on the whole space if you don't like tangent on the sphere. Then the summary statistics are now two things. You have the overlap, the latitude, this projection. You also have the radius, right? The distance here. It's like on the sphere, but a thickened sphere, if you want. So you have now two-dimensional summary statistics. Okay? So that would be, of course, in the case where you don't know a priori that your signal is of norm 1. Right? You don't know the norm of the signal, and you estimate both, the norm and the angle. Okay, so when the step size, when the step size of your is below critical in your SGD, you have convergence to this dynamical system, which is very simple. When it is critical, then you have additional fixed point, and there are all sorts of things can happen. I will not be specific here. But let me just say that when you initialize randomly, which means in the sphere you initialize near the equator, so the SGD starts in a microscopic, as I explained, neighborhood of an uninformative fixed point. And the effective dynamics, there is a sharp transition depending on the signal to noise ratio. It's either a stable or an unstable Ornstein-Uhlenbeck in dimension 1. So which one is good? Is it stable or unstable?
Unstable.
What?
Unstable.
Of course, unstable, right? You have to go against the grain. Normally, good Ornstein-Uhlenbeck is stable, so that you have an equilibrium. Here, if your Ornstein-Uhlenbeck in this direction is stable, it means that your algorithm stays at the equator, and so stays stupid, right? So you want it to be unstable, to move away fast from the equator and find the latitude that you want to find. Okay. Now let's generalize a little bit, because that was very simple. For that, we didn't need the notion of effective summary statistics. It was just dimension 1. So let's take the simplest thing. Now take multi-spike, right? So now the tensor you want to estimate is not one spike, but R spike, right? And you have a signal to noise ratio lambda j in front of each of them. And then you have noise. Okay? Very simple, still very academic model. Shouldn't be too hard, right? So you do the same thing. You do the MLE estimation, like we explained here. And here we obtain this. Here you obtain something more complicated, but which is still related to spin glass things. So this has been done. So going back to the topological question, this has been done by Vanessa Piccolo, a student of Alice Guillonnet and myself. And you have this in a paper which is now a year and something old. Now you have to minimize a complicated random function on a product of spheres, right? Because you have now to estimate U1, U2, U3, etc. Right? So you're on a product of sphere. The topology is so. This works. So I told you briefly how you compute the topological complexity of a random function. You use the Katz-Rice formula, which is an exact function, exact formula which gives you the number, let's say, of critical points or local minima, in terms, and it's a dictionary with random matrix theory, right? Because in the Katz-Rice formula, you have to understand the determinant of a random matrix, which is the Hessian of this function conditioned by the point being critical. So this thing defines, again, a random matrix model, which this part will give us something which is invariant by rotation. The part coming from this thing will be essentially a GOE, but now you have a multi-rank perturbation of a GOE. So this is studied by Vanessa. This work in the multi-spike asks for results which are, so the basic thing that was needed when you had one spike was a large deviation for the top eigenvalue of a random matrix when it has a signal. Okay, so you take a random matrix, you add a rank 1 signal, and you ask for the top eigenvalue, the large deviation of the top eigenvalue. That was the important thing. And that we had done a long time ago. But this one asked for very hard work by Alice Guillonnet and Husson. So this is a little heavy. So that's in some sense this is cool if you like random matrix. It's seriously hard, but you cannot do that for every model because it becomes really difficult. So anyway, now let's forget topology. And of course, I didn't say the result, but the results are as you imagine. You have a region of mediocrity, chaos, lots of random, lots of critical points, and then you have things like this in all those spheres, and depending on the signal-to-noise ratio, everything can happen. Okay, so let's look at the optimization now, because that's practically what we're most interested in. So, in this joint work with Vanessa and Cedric Gerbelot, a postdoc at Courant, and now back in France, which is almost a year old. So we consider this, the SGD for this. And to simplify, we take the spikes, the signal, to be orthonormal, right? We don't want two spikes to be very near. So we take them to be orthonormal, right? They are on the sphere and orthogonal. And then we look at the natural line SGD. So the natural line SGD here are on the Stiefel manifold, which is the manifold of R frames in dimension n, right? So the set of matrices like that, because in fact what you're trying to estimate is an R frame. So, and you now ask again, so you have this natural dynamics on this manifold, and you ask, how many samples do you need to recover the spikes? So this will very much now the question, so why is that, I mean, it's just, why is that more interesting than one spike? Because now you have the story of possible confusion, which of course we want to understand. In the end, we want classification of cats and dogs, right? But now, if the signal-to-noise ratio, even though I assume the signals to be orthogonal, which is natural, of course, when you pick signals at random, they will be orthogonal. There is still an element here, which is the strength of the signal-to-noise ratio, right, for the different signals, right? So depending on this, so this will depend on the separation of the signal-to-noise ratio. I will call lambda 1 the largest signal, lambda 2 the second largest, lambda r the last one, the smallest one. And this will depend whether we are in p equal 2, the matrix case, or p larger than 3, the tensor case. Here, the natural effective dynamics work in dimension r, right? It's natural, we have r spikes, but at least this is at the end of training. This is once, I don't want to describe what happens in the so my 17 here is R. But there are regimes where, before that, where you maybe don't see the R things, or you see more than that and they are completely fake. All sorts of things can happen in the beginning of the optimization procedure. Once, or equivalently, all things can happen if the signal-to-noise ratio are not strong enough. If they are strong enough, then things will simplify like this. And so in this case, you see that the summary statistics seems reasonable. You want to project in the dimension of the spikes, of course. So here are some results, if you're interested. If p is larger than 3, so we are in a tensor case, and if the step size is chosen smaller than this, n to the minus p minus 3 over 2, and if the sample size is larger than that, then we have full recovery of the spikes if the SNRs are sufficiently separated. So in this case, you find, if you had the 17 spikes, you find the 17 spikes as precisely as you want. Okay? So you see, you need enough data size, because that's what is imposed by that too, in fact. Right? If you take a, okay, so let's move on this. So this is if they are sufficiently separated. Let me stay with that for the moment. I mean, this series of papers with Vanessa and Cedric is like 120 pages, so I'm summarizing in one slide. There's enormous number of things that can happen. But let me just keep this. So if the SNRs are not sufficiently separated, then of course you cannot recover the spikes. You don't know which one is which. So you can recover a permutation of the spikes, obtained under a very specific greedy elimination process. Imagine that the signal-to-noise ratio are all the same. How do you know which one is 1 and 2 and 3? There's no way, right? So there's a random permutation obtained under a sort of thing. In the case of matrices, things are similar, but the thresholds are different. You have logs everywhere, like And okay, that's the result. So okay, I can. So this is just a little bit of a taste of what can happen when you have multi-dimensional signal to recover, right? So of course here the dynamical system you obtain is not that complicated, right? Because you've seen the structure, the things are very separated. The only confusion you get is when the lambdas are the same, or close to the same. Okay, so that was a natural multi-spike. Let me give you multidimensional effective dynamics. Let me give you another example. Let me give you the XOR of a Gaussian mixture. So Giulio told you about the binary Gaussian mixture being for computer scientists the equivalent of Curie-Weiss or Ising or whatever. So of course, if you're a physicist and you understood Ising, or let's say Curie-Weiss, then you want to complicate it a little bit, right? Because Curie-Weiss is cool, but you know. So this is what happens here. So XOR means exclusive OR, right? So you know what exclusive OR means, right? So we study here this Gaussian mixture version of the classical XOR problem. So here it is. The XOR problem is arguably the canonical example in computer science of a decision boundary requiring at least 2 layers in a neural net to represent, right? So why is that important? Because this is what created what they call the second AI winter, right? You know, in artificial intelligence, you had winters, which mean they were very happy, things were working, everybody's very excited, and then boom, something doesn't work, and it's a winter. And then it goes down, and then at some point this is solved, and then it's summer again, and then it's winter again. So right now we are in the summer, as you've noticed. But this was a winter, so why was that? I will tell you what the XOR problem is, but it needed 2 layers, but they didn't realize that it was the time of success of physics. They had understood what the perceptron does. Perceptron is 1 layer, right? But with 1 layer, you cannot solve XOR. So that was, and then suddenly said, oh, why don't we put 2 layers? And then things work again. Okay, so that's why it's a classical problem for when you talk to these people and you mention you did something for XOR, they are like, because it's a serious problem for them. It was at least. So here's the question. The data is given by an IID sample, yi, capital Yi, little yi and xi. So the yi's are Bernoulli 1/2, I mean, coin tossing, 0, 1 with probability 1/2. And the xi's are given by Gaussian mixtures. So when y is 1, where your thing, let's say, is red, then x is a mixture of 2 Gaussians. Here, to simplify, so you put it, let's say, here with a center mu and negative. So and so here, around each of them you have a Gaussian, right? That's what we have here. Mu with a Gaussian with variance 1 over lambda. So when lambda is large, this Gaussian thing becomes small. Okay. And when y is 0, when your object is blue instead of red, then you have nu and negative nu. Okay, so the blues are here, the reds are here. Okay. So you see, it's a little complication of a binary mixture. But so you want to classify. I'm sorry. So what you have here is a supervised context, right? You get your draw from X, and somebody tells you it's red or it's blue. Okay, because you're given the little y. And now you want to classify. So you observe, and then you want to know is that red or blue. So the way to do it, the one that has emerged after the winter, was to do it with a 2-layer network and the cross-entropy loss. So do you understand this notation? So a 2-layer network here will be with, so what here, this is of size n. n nodes. Here you have k nodes, right? Here you have weights. On each of these links you have a number, which means in good French that W is a k, good English, it's a k by n matrix. And then what, so what happens here is that you have your vector x which comes in, it's an n vector. You multiply it by this matrix which is k by n, right, which just means that you're taking the linear combination, that's the linear part of your neural net. Then you get here, you get a k vector. You apply to this k vector, so here you get wx. You apply to this k vector the function g, and this function g is applied pointwise. That's the basis of neural nets, right? At each thing here, you apply g. When you have a vector, you look at g of x1, g of x2, etc. And then once you've done this, so here you have the nonlinearity g. Once you've done this, you have another thing which I called v, right? Because it's a vector, because it ends up with one node. So it's a k vector. This gives you v inner product with this thing, and then this gives you something, and here you apply sigma, which is another nonlinear function. Okay? So that's the best architecture you could do. And here sigma is the sigmoid, which is natural when you want to have something that will be, you want the output here to be a 0 or 1, right? Red or blue. So sigmoid. And G is the ReLU activation factor, rectified linear unit, which simply means x plus. Okay? So what does this gives you? It gives you, if I give you a vector x, it gives you a number y hat of x. Right? So this defines a class of functions. Right? If you take all the possible w's, all the possible v's, this defines a class of functions. Right? And approximation theory tells you that with this class of function, you can approximate many, many things. And in particular, this classification problem that we have. So then you have to choose an optimal such function. And to do that, you put a loss. The loss you put is a cross-entropy loss, which means, oops, the loss is given by this. Believe me, that's what you should do. So it's here, this term I added is, of course, you see what it does. It's because here I have these vectors v and w in possibly high dimension. I want my system to be stable and not to escape at infinity. So I add a harmonic potential, the bounding force, to keep them there. And of course, this alpha is to my choice. So I invent nothing here. This is 50 years old. This is the loss function. You see, this is a complicated random loss function once you take the empirical version of it. So, but if you look at the law of this thing, you see that in fact it is, of course I didn't say something. Here, this n will be very large. That's the idea, of course, of neural net. This n will be very, very large. But a priori, the way this works is this k doesn't have to. So in the classical version, k is 4. Right? And then when k is 4, if you look at the law of the loss, it depends, you just look at it, and it depends on 22 parameters. Okay? So it's natural to assume that maybe there are summary statistics in 22 dimensions. I mean, if you believe that nature is not too bad, right? So, in fact, there is summary statistics in this case. I won't show you everything. They are, in fact, lower than this. They are dimension, I forgot now, something like dimension 13, because you have, in fact, a certain number of those dimensions that are not very useful. They don't move fast. But anyway, if you do this, the summary statistics and the effective dynamics of this are crazy. Okay, the dynamical system is like, wow. So I just show you a little bit. The effective dynamics in the ballistic regime exhibit a rich phenomenology. There are 39 fixed point regions. right? In this example, I had 1, right? It was in the neighborhood of 0. Here you're in dimension, I don't know what, and my 17, I'm not sure it's 17, I forgot, 13. And you have 39 regions which are critical, which means slow. If you get there, or if you start there, it's like our 0 here. It's mediocrity. You have 39 places where you have to escape mediocrity, right? Where there are 39 ways to be mediocre. And they have various topological dimensions. Some are lines, some are planes, some are points. And 24 of them are stable. The stable ones are the ones you don't like, okay? Except for the neighborhood of the minimum, right? This is a stable place which is hard to escape, and you don't like that. You want your algorithm to not get stuck there, right? So, interesting. But what can you do with that? You say, how does this work? So what does this say about the algorithm? So if you initialize the weights randomly, so here my random function, it's random because these weights, W and V, are chosen randomly, right? That's the data, that's the random thing. If you initialize this, your network randomly, like you have no information, say with a Gaussian distribution, then the algorithm will converge. The algorithm will be good in short time, will converge to a classifier, will be bad, I'm sorry. Converge to a classifier with a macroscopic generalization error. That is a bad classifier. Something bad, it doesn't classify. With probability 29 out of 32. And then it will follow a degenerate diffusion, something it will just wander around and do nothing good for a long time. Of course, if you wait long enough, it might escape this thing. Okay? Which means that the system works with probability 3 out of 32. Okay? Because of this complexity of the limiting dynamical system. So what happens is you have this crazy system in dimension whatever, 13, and then when you start at random, now here, when we started at random, we had one bad region, right? Which was here, the equator, this point. Now you're in dimension 13 on this side, and in fact you have many more bad regions in the projected space. If you start at random, and if you start in one of them, so out of these regions, you have one which is good, the one that contain the real minimum. If you start from that region, you're okay. If you start from the others, it will take forever because they are, or if you start from the unstable one that lead to the good one, you're okay. But if you start from the bad ones that are stable, then you're not okay. And the probability to start from a bad one that is stable is 29 out of 32. Right? So this is what gave us, I was bragging, you probably saw that that gave us the best paper award in the computer science world, because for them, this was like, wow, because of course they knew this type of things. But and for me, it was a big first because I've never in 40 years of probability computed a probability of 3 out of 32, except in problems for kids or, but okay, so that's what happens here. This sounds crazy, but of course, this can be, so the probability of a good classification is 3 out of 32, and this is the important characterization of the statistical procedure chosen to classify. Here, the structure of the XOR network, the one I'm writing here. Of course, you may not be satisfied because, so first, just to check, is this good news or bad news? It's good. Why? Because 3 out of 30, okay, you could say 3 out of 32. Ugh. But remember, here you should not think like a physicist or a mathematician, but like a computer scientist. What you want is to train your weights once. So here this tells you that you have roughly 3 out of 32 is like 1/10. You have 1 chance out of 10 that your training thing works in decent short time. So just do it 10 times. Right? That's okay. Of course, if you say that and you're really training a huge system, then you don't do train time. You don't train 10 times. But here it's not that bad of a news, right? But you still may want to say, okay, I don't want to train this 10 times to find one thing that works. So there's an obvious solution, which is, of course, as always in machine learning, it's over-parameterization. So here, nothing forces us to have k to be 4, right? And this 29F32 is linked to 4. If now you let this second layer go to infinity, you over-parameterize, then this probability goes to, this thing becomes much less fun, at least to tell. The probability goes to 1 exponentially with k. Okay, so the probability of success becomes 1 minus exponential minus k. Okay? So then...
And your summary statistics, or I mean, your 22 parameters...
Of course. Of course, it's, instead of 22, it becomes whatever depending on k, but you also have a trivialization, a topological trivialization, like I explained here, and you have your system now doesn't have that many stable things.
It remains around the same ones for k equal 4, or it changes a bit.
The region?
Yeah, no, I guess the region changes.
No, the region. No, because of course the space grows, but the probability, when you start at random, you start from the good region. That's what it says. You still have a lot of things, but when you start at random, you avoid the bad things. Okay? So over-parameterization can be good. All right, so that's a simple example you can remember, that things are not necessarily dimension 1. Right? They can be much richer than that. Okay, I won't do that. Let me go now to the example that really motivated the whole story, which is the classification of Gaussian mixtures. So now I will take a k Gaussian mixture. And now this is not a simple model. When you take 2, it's simple. K is not simple. So you do the following. You have the same story, but so it's not like that. You have a mixture of Gaussian. So here I will assume, to simplify, that the covariance of the variance matrices are just isotropic. 1 over lambda is the variance, so lambda is a signal-to-noise ratio. Mu A is the center of these Gaussian peaks, and PAs are the proportions. Right? So it's not 1/2, 1/2, it's whatever. So mu A is being a flower, being a dog, being a cat, whatever, and PA is the proportion of all this thing in your images. So to simplify, we assume, of course, the means are linearly independent, otherwise it's a pain in the neck. So you are in dimension k. I assume that there were k components. And you try to perform the classification task. So again, you have to choose a procedure. You have to choose something. Here we choose the thing that is typically done in simple, and that was the established religion 10 years ago. Of course, today things change. But so you do that with, let's say, a single layer network with k versus all versus 1 classifier to start. Then I will do multi-layers, but for the moment, single layer. Using a cross-entropy loss and an L2 regularizer. So here I didn't write the L2 regularizer. So in this single layer network case, the loss function is this. It's equivalent to logistic regression. So you have this function. Okay. So what are the x is your parameter. What is y here? Of course, the data you have is you have a mixture of Gaussian, but it's supervised. So somebody tells you, with the little y, it's 1 or it's 2, or which means it's a cat, it's a dog, it's a flower. You have that in your supervised training part. And these are the one appearing here. Okay? And x here is the parameter, so x is in the space R to the D. It's like the center to the k because you have k centers. Okay? So you are in this space, you want to minimize this thing. Can you find good summary statistics when the means or the peaks or the mu's are well separated enough, or equivalently when the lambda is large enough, which means this covariance, the peaks are sharp? It could be the projection on the space of means, naturally. You think of that, right? But it could be something else. So again, we study this thing. I'm sorry. So here, I stop there. I mean, I don't stop there, but this is the question. I will come back to this question after I've told you more seriously what summary statistics are and how you find them. Okay, so now this is a motivating example. I gave you examples where we knew what to do. And in this one, we'll wait a bit. All right? So What are summary statistics properly? So again, I come back to the notation. So the projection, so I mean, if I will try to be fast on that because it's purely mathematical, but so the projection here, and purely Bourbaki-like, there's no information on anything, just what does it take for something to work? Okay, so function u will be my projection. It's a smooth function from Rp, the space of parameters, to Rk. So this is 10 to the 9, this is 17. So that's u. And the importance is to understand the evolution of this projected system, u of xl, when possible. So to develop a scaling limit, I need some assumptions. So I call h, this is the loss function. I call h the centered loss function. Remember, this is the population loss, which is the expectation. There's no n here. So this is just the centered loss. And I view h as a random function. It is a random function. And I will call k its gradient, and v the covariance matrix of this gradient. And then I say that a triple for this projection, the loss, the unknown probability distribution, is delta localizable if you can exhaust the whole set by compact sets such that you have all these conditions. All right. Okay, I don't expect you to swallow them. You see what they are. They are all conditioned on sizes of derivatives. And believe me, they are the ones that are supposed to be done, because if you do less, it doesn't work. If you do more, you're wasting your time. Okay? So, and of course, you see that all this thing, soup of derivative of this, derivative gradient of phi, gradient of the centered loss, and whatever, look at the right-hand side of these inequalities. They depend on the inverse of delta, where delta was the step size. So this tells you that given a bunch of given a loss, if you choose delta small enough, these things will be true. Right? If you choose delta small enough, all these things should be true, because you have delta to a negative power on every right-hand side. But that's a quantitative thing. It's not delta tending to 0. Right? It's quantitative in terms of the landscape you're trying to explore. Right? Because on the left-hand side, you have the function h, phi, whatever. Okay? So now I call J the Jacobian of the summary statistics, and I introduce these two differential operator. This is the gradient of the population loss. Remember, phi is the population loss here. And this is this second order operator. V, remember, was the covariance of the gradient of the centered loss. All that is perfectly meaningful. And so now I take my SGD initialized with the learning rate delta, and I suppose that this triple is localizable, which means in a good way that delta is small enough. Then, so I look at u of t, the linear interpolation of my, remember my SGD is defined at discrete time, so I linearly interpolate to get a continuous time process. And then I said the main result is that this thing, so these summary statistics are indeed asymptotically autonomous. They converge to an autonomous ODE. In fact, SDE, you have here a drift term and here a diffusion term. Okay, so this is the result. If you have this condition of localizability, which means delta small enough, okay, and if where was that? Oh, I didn't give you where h and sigma are. They are, of course, obtained from these two operators that I call A and L. Okay, I'll come back to that because it's needed. So these are possible examples. I won't be there. So before I go to being more precise, so okay, this tells you, so this abstract nonsense theorem is valid, could be valid anywhere for any scale. I mean, you could have, nothing tells you that summary statistics are unique. Right? You could have all sorts of projection that works. Right? The important criterion is, of course, that the projection you choose tells you about something about the performance. right? So in the end, it should contain something that essentially now allows you to compute the cost, the loss, right? But you have all sorts of things that, so nothing is unique in this thing. And again, if you do it in different regions, you can even, as I said, change the time scale, change everything. So maybe I won't go there. Let me forget this thing. Okay, so let me compare this with the classical limit theory of SGD. So, yeah, because the condition I didn't tell you was that, but okay, we'll see here. Let's assume here that the term A of u and the term L of u multiplied by the time steps admit limits, let's say f and g. The condition I didn't write is that I wanted that the difference of those two converges to something which I call h. Okay, that was my drift term. But in fact, you could get it by these two being separated in f and g. So this is what I'm saying here. AU minus f of u goes to 0. So AU is essentially f of u, and delta LU is essentially g of u. So this is very natural assumptions for what I want to do. And then in this case, my drift term, h, is in fact minus f plus g. F is called the population drift, and g is called the population corrector, and the diffusion matrix that I had in the equation is called the diffusion matrix of u. Okay. In the fixed dimensional perspective, in the one that when the dimension is fixed, what you suppose is that in the end, u will be, again, you have the gradient flow of the population loss. Being a summary statistics here means simply that u will follow this equation, with just f, right, which came from the population loss. Remember here? This is what f was. Of course, you've forgotten what a is, but that's what it is. And so in this perspective, this perspective applies in what we do in the high dimensional situation when the population corrector G and the diffusion matrix sigma are 0. Right? So we have a result which seems to be much wider than what happens in the classical regime. But this should be the canonical thing that happens. The appearance of a G and of a sigma should be bizarre. Okay? So in particular, you should predict that when the time step is small enough, this is what we should get. We should get the classical picture. We should not have a G, we should not have a sigma. Okay, and this is what happens. So in the subcritical regime, there is a scaling of the learning rate. So there is when the learning rate is smaller than something, as I explained before, then we have the limit, and it's G equals sigma equals 0. That is, we have the same thing as for the classical picture. Right? It's just like, it's what's coming from the gradient flow of the population loss. And we call this the subcritical scaling regime. So if the time step is small enough, then this thing applies. I remind you that you cannot necessarily take a very small time step. Right? That depends on how much data you have. But then there is the critical regime. So what I don't say here is that, so you have a critical value, which is the edge of stability, and above which nothing converges. The system is very unstable. I don't know how to quantify unstable, but it is unstable. Some people say that it's good to be in the unstable regime. I don't see why, right? So, but to be honest, some people say, yeah, it's good. What I believe they say is it's good to be at the critical scaling, just at the edge. So when you're at the edge, then this G and sigma are non-zero, maybe non-zero, and you have non-trivial correction to the classical picture. So to understand this, it's easy to see that the condition I gave you about localizability, if it's true for a delta, it's true for a smaller delta, because everything depended on negative powers of delta. So if something's nice, a smaller delta is even nicer. And it's easy to see that if you have a limit theorem for delta, if you take a smaller delta, much smaller delta, then you will still have a limit theorem, but necessarily the G and the sigma will be 0. It's easy to check. So in this subcritical phase, these extra terms are not there. So there is only one scaling of delta at which G and sigma may be non-zero, and this is the edge of stability. So, okay, the ballistic limit is this, as I explained. I don't want, okay, let me just go above this. You understand what diffusive limits are. Let's forget all that. What I mentioned is now the following. Let's just mention very quickly. Imagine that now in this projected dynamics, you have a critical region, maybe a critical point, like this one. Right? Then, in the time scales where you are, this thing will just essentially stop there, or not move from there. So what you can do is rescale time here. Right? And then you can, applying the same abstract theorem, the same Bourbaki-like theorem here, obtain what is called the rescale diffusive regime, which gives you now, in a different time scale, which means usually more data, you spend more data to get away from this, you find a different equation which would explain how you escape. So here it will tell you, in a certain time scale, for instance, you would have just this. If you go to a deeper time scale, you would have one more term and maybe a diffusion term that allows you to move away, as I said when you had this Ornstein-Uhlenbeck thing. So these rescaled effective dynamics are important. They are not important to understand in the first step, but they are important to understand if your system is trapped somewhere. It tells you how much more time you need to escape those things and how you will escape them, and how much more time here means how much more data. Remember, because each time step is a data point. Okay, so this tells you, okay, my system doesn't work, the performance is not good, it's stuck somewhere. How much more data do I need to unstuck it and so that I get to a point where it will work? Okay, I will skip all that. Okay, so now, I still have 15 minutes, right?
Yeah.
Good. So now back to the question of that was asked at the beginning. That was, okay, in general, so I told you, I gave you example, this cute XOR thing, which is completely crazy, with, of course, Tensor PCA, multi-spike Tensor PCA, blah, blah. But in all these things, you could guess and follow natural objects. But in general, how do you know that there exists summary statistics? Does the system know that there exists a finite dimensional projection in which things happen? So one way to test that is, of course, spectral. And that will be what I call the dynamical BBP transition. So why spectral? You have here, remember, we have, let's ask the question first, not even dynamically. Let's ask it topologically. I give you you have a function f of, let's say, n equals 10 to the 9 variable. Smooth, of course. Okay, a nice smooth function of a 10 to the 9 variable. And you want to say f is in fact mostly a function of 17 variables. Again, I'm coming back, all these intuitions come from basic statistics of the 18th and 19th century. So how would you state that? What does that mean? That means that if you draw a picture of your function, in 10 to the 9 minus 17 directions, it's essentially flat. Of course, it's not flat, but its derivatives are small compared to the derivative in the 17 directions. So it means you have serious derivatives in 17 directions and not so serious derivative in 10 to the 9 minus 17 directions. How do you see that spectrally? You compute the Hessian, right, at the point. You look at, so the Hessian is a matrix of 10 to the 9 by 10 to the 9. You look at this, it's a real symmetric matrix, it has a spectrum. You look at its spectrum, and but when you say that you have 17 directions that are really curved, it means that these eigenvalues should be very much outside of the box. You have 10 to the 9 direction minus 17, which are flat, where these eigenvalues should be smallish, right? Smallish with respect to the others, of course. They can be large, but not as large as the curved direction. So you have 17 directions which are curved, where the eigenvalues should come out of this. Okay? So spectrally, you look at the spectrum of the Hessian. That's simple. Right? And so that's the BBP transition in random matrix. It's situations, the classical models coming from statistics or physics of random matrices, the eigenvalues are packed together in bulks. You all know the semicircle or the Wishart distribution, whatever. And typically for classical random matrices, the top eigenvalue sticks to the bulk and the lowest eigenvalue sticks to the bulk. Right? They are. But when you have a signal, when you have this, then maybe you have a few outliers out. And that's what the BBP transition does. Okay? Now, in my thing here, where do I compute this f of x? Right, so remember, we're already computing the Hessian to understand the topology through the Katz-Rice formula, the Hessian condition by criticality. But here I won't condition anything, but in some sense I do condition. What x do I choose? I cannot choose the critical points because I don't know where they are. So what do I have access to algorithmically? Essentially only my trajectory, right? So I move along the trajectory. I could look at some point along the trajectory. I'm not saying that algorithmically it's easy because computing a spectrum in dimension 10 to the 9 is heavy, right? But at some point you can look at where you are. Do I have good directions to follow? Then I look at the spectrum of the Hessian here. Okay, that's one possibility. Another is the Gramian possibility, which means, you know, in random matrix you have two big models: Wigner, IID entries, and Wishart, which means XX star, the statistics example, right? Which means in more abstract math, the two types of free convolution, additive and multiplicative. So here, same thing. This would be the additive side. This would be the Wigner side. You could also try to look at something on the multiplicative side, which means the Wishart side. So what would you do? You take the gradient, but if you take the gradient at one point and take the gradient transpose, this will be a rank 1, so there is nothing to say. So what you do is you take your gradient at every step of a long stretch of your trajectory, and now you have, and you take this series of gradient and multiply by this transpose. This gives you a random matrix of Wishart type. And possibly they also identify the same outliers. What is the interest of the second procedure compared to the first? This procedure is much less expensive computationally because the gradient, in order to do the gradient descent, remember you have to compute the gradient at every step. So you have the gradient. You don't have to compute it. You just have to store it for a while. You store your gradient, do your matrix, compute the spectrum, not that easy, and then see if there are outliers. And then you project in those outliers, hoping for the best. Okay? So that's what we'll explain here. So the next question is to find this summary or statistics and the effective dynamics to show that they are autonomous. Of course, I'm starting from the idea, if you have outliers, the dynamics should be autonomous. This is a question of faith here, right? But in fact, of course, you imagine you can prove something like this. So try to follow the spectrum of the Hessian or the Gram matrix along a part of the optimization trajectory. What some people do, you don't even have to look at the whole Hessian. You could look even at Hessians of layer by layer in your random function, in your neural net. And you have different structure there. It's a long story. But let's continue with that. So in the right regime, wide parameter zone, then you can hope for a BBP dynamical transition where you have outliers. This is what I just said. So this was done numerically by Papian 7 years ago. And he was a student of David Donohoe. And then they wrote a paper together which is called Neural Collapse on the numerics of that, on seeing that this spectrum was... The experiments there were not huge, but sufficient to be convincing in one example. And this is done rigorously for more complex tasks and deeper network in this work with Reza Gheissari, Aukosh Jagganath, and we have added Jiaoyang Huang, who He's one of the very best experts we have on the random matrix side. So we study the interplay. Let me just, I don't want to give you too heavy theorems, but essentially I already gave you the theorem. So the interplay between the training dynamics via SGD and the spectral composition of the empirical Hessian and maybe the Gram matrix over the course of training. So we follow that in two canonical tasks. I will explain here two canonical tasks, the KGMM and XOR, right? And I could do XOR with more than two, just if I want to be complicated, right? So we could also do that. But let's think XOR with two because I already told you what that was. So here's what happens, both numerically and provably. Shortly into training, not immediately. When you start, again, you start in mediocrity. So you start, you know, if you take, in this let's take this example, by the way, to understand the spectral transition. What is the Hessian of this thing, again? We already mentioned that. That's the Hessian of that thing, which is something like a GOE. And then you add the Hessian of this thing, which is just rank 1, right? So you have a random matrix plus a rank 1 perturbation, okay? And of course, the eigenspace corresponding to this thing is, of course, the one you want. And in this BBP transition, the eigenspace to this top, when the lambda is large enough, so you have a transition, in this case it's perfectly easy and understood, it's very close to the original BBP transition. When lambda is large enough, at some point, the outlier comes out of the semicircle. Okay? Initially, it doesn't. That's the important thing. The important thing in the BBP transition for a mathematician, it's that it's a negative result. First, it says you may have a rank 1 perturbation and nothing, and the spectrum just eats it. And initially, when we were saying that 20 years ago, it was like a mystery of large matrices. But in fact, in this context, you understand that it corresponds to what I was saying. There is a regime of lambda where you cannot, even information theoretically, capture the signal. So you cannot capture it spectrally. You cannot capture it in any way. So it's normal. So there is a phase where the outlier is captured by the bulk, and then there is a phase where the outlier comes out and then goes away, right? And when it goes away, the eigenvector associated with the outlier aligns with the signal. Okay, this is what happens here. So this is a global picture. And so here you see that you have C of k, not k. You may hope that to have k outliers, because that's the dimension of the signal you want to capture. And more importantly, so what happens is that you have this outliers, this eigenspace corresponding to these outliers, here of dimensions certain constant dependent on k. And SGD essentially works in this direction, right? So you have this summary statistics. The C of k is explicit, depends on the model, the performance, blah, 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 but I will not get too much. When you do multilayer, I didn't explain how you would do multilayer, but you all know that classification is done with multilayer network. So the same thing that I was describing here, but more than one layer. Then you see that the alignment happens within each layer. And so that's because, you know, now when you have this, when you have a multi-layer thing, your Hessian has naturally a block structure, right, for each layer. And each block aligns with what it should align with. But beware, this alignment is not predicated on success of the classification task. When sometimes the SGD converges to a suboptimal classifier, to something not good. Then the empirical Hessian and G matrices have lower rank outlier eigenspace, and the SGD aligns with those bad spaces. Right? So it's not a sign of, it's intrinsic, but it's not a sign of success. That's if you don't have enough signal. So let me explain this in this particular case. Yes? Yeah. So that's the case I wanted to finish with that. That's the classification of KGMMs. That's what we said. That's the loss. And now, if I take a learning rate, which is capital of 1 over d, the SGD aligns with the outliers of the Hessian. Here's a theorem. There exists, so this gives you quantitatively how many data you need and after how much time. You see that here this tells you that the SGD in block C lives in the eigenspace of the block of the Hessian of the loss function, and the size of the error. So it says it works. And this follows from a theorem that describes the SGD trajectory, its Hessian and its Gram matrix up to a certain error. So the following live in the span of the, if your signal to noise ratio is strong enough, then the following lived in the span of the means, which is what you want. The state of the SGD, so your algorithm, the blocks of the Hessian, the blocks of a Gram matrix, all is there. So this subspace captures everything. But inside the low rank space spanned by this means, the training can be complicated, like we had in my XOR model with a lot of critical points and so on. But, okay, I will not spend there. Let me just finish with this. So I'm just telling you, this abstract nonsense thing works in the case that was the initial motivation, which was classification of multi-Gaussian. So here's a few questions. Can one see a true, but here what I just described is if the signal to noise ratio is strong enough, right? So, but I didn't describe a transition, whereas the BBP transition is really a transition. You see something bad and then something good. Precisely. So can one see a true dynamical transition and the emergence of the outliers? And should one really care? So the situation is really interesting and murky for our examples. One interesting basic factor that the BBP, so as I said, this is negative. So can it be that the spectrum fails to expel the outliers, even though they are there? Yes. Right? As I explained here, it's first negative. It can be that you have a signal and you have no outliers, like in this example. Can it be that the spectrum fails to expel the outlier, but that the SGD still works? In general, in this example, no, but in general, it can happen. When the spectrum spits some outliers, are we always happy? No, because sometimes these outliers have nothing to do with the real thing, because we are not in the right part of the space. We're exploring this big dimensional space, and the spectrum does something here, but we are not yet in the right place. So at every point in the summary statistic space, is there a BBP transition for the spectrum? Yes, you always have a sharp transition at every point. But we don't of course sample every point. We just explore that through a path. Can we prove this transition is sharp all over? No. It must be true, but we cannot completely prove it. So you have a transition. In some places it's sharp, in some places it's, we don't know. If you want to work on that, please do. Is it sharp at initialization when you start at random? Yes. So initially you really know what is the strength of the signal that would expel outliers, like we had here. Does the SGD dynamic, this is the most important thing, improve the BBP transition along the dynamics? Yes. That's the crucial thing. You move in a direction where your BBP transition is better. Right? Okay, that's of course what the algorithm wants to do. And that's the end.
Thank you very much. Thank you very much for this nice course. Are there questions?
Yes, please.
What's the take-home message for the last two slides? Because there are many things that you say actually it is not good enough.
What is the take-home message for which one?
The take-home message for the two last slides.
The two last slides. Yeah. So one is, of course, when your signal-to-noise ratio is strong enough, everything's nice. Right? There is a threshold. So that's the take-home message for the engineer who is afraid. Right? Because if you have enough data, at some point, this transition is exactly like we had here. When the signal-to-noise ratio was large enough, you saw all this mess that I was describing initially that disappeared. You had topological trivialization, and the algorithm would just go there. So this always happened in this low-dimensional space, right? And they characterize the performance. But what the message is that you could see, for instance, in this multi-spike tensor, you could see there is an intermediate phase where you should be prudent. That's what I'm saying. You see, for instance, outliers coming out. Oh, great, I'm done. And then they come back in, right? They are like sheep coming out of the herd. And then, oh, no, finally, I'm not happy out there. I go back in, right? And so careful. That's what the take-home message is, be careful. So this is what the, but that's not too hard to check, because if you look at the dynamics in this projection thing, it doesn't help your SGD. Right? That's, so there's a moment where really things go out, and of course this depends on how hard your task is. Again, if you take the multi-spike tensor PCA, if your lambda, it depends on the distance between this. If your lambdas are all, the signal to noise ratio are all sufficiently different, you don't have this kind of craziness. But when they are together, you could see all sorts of bad things happening. Right? That's, so when your signal is ambiguous in some sense, naturally, this emergence of a simplified version takes more. That's the take-home message. So the take-home message is be prudent if you do something with it. If you, for proving it's cool, the take-home message, there's a whole region of things that are crazy that we love to study, right? But if you want to apply it to, you have to check that your thing is not crazy.
Okay.
So just in practice, what sorts of problems is this good for out of the box? So is it like images, learning physics, like public health data? Just in practice.
OCAMS tells you everything. I don't believe, of course it doesn't mean that it's easy to find, but I do not believe that there is anything in optimization that works in dimension 10 to the 9. There's not one. Every model I try, every time there is a low-dimensional thing that works, at least when you have enough data, it's always there. It's the basis of statistics. It cannot be otherwise. You know, nothing is a spin glass. Right? Apart from the spin glass. Do you try to infer something from spin glasses? I mean, no. So if your system is supposed to work and works, then it must work in low dimension, but you don't know which one, it's hard to find, etc. That's the story. And you can find these low dimensions spectrally.
Maybe a last question.
Okay, look, there's somebody else. So you discuss this edge of criticality with respect to stability. Sorry, with respect to delta. When you add one sample each time, I guess in practice they use also mini batch, which must stabilize the noise. Is it what is the good thing to? There must be a trade-off also between the two.
You're right. I'm sure that if you do a mini batch of size, whatever k, I'm sure there will also be this phenomenon of edge of stability, and you're probably right that in some models it might not be the same when for k equal 1 and k equal 5. But that I didn't. I've never studied. You know, I on purpose, as I said, studied the extreme case of online because that's as far as can be from the simple thing, which is supposed to be the full batch, and because also it's practically better. Right? It's much easier to do one at a time because you just take a data point. So.
But the nature of the noise will change.
The nature of that, I agree with that. I've had, I'm sure this is true, but I cannot answer that. That I don't know. But you know, this whole, and there is another question of the same nature, because what people do, as I mentioned at the beginning, they not only use mini batches, they use online. They use online a lot, but they use mini batches. Nobody uses large batches because it's just too heavy. But they use mini batches. So this choice of mini batches is an engineering choice, and I'm not an engineer, so they just smell their thing and they know that the mini batch should be of that size. I don't know how they do it, but so you're right. This might be an answer. This might be the reason why this mini batch is better than that. But there's another thing that they do is reuse, right? So you do what I just said, let's say online, and once you've finished to use your data set, you're somewhere, and then you say, okay, I need more data, I just reuse the same data. Right? I just go for one more pass, and maybe 10 more passes, and then, right? So, and they do that, and they try to not do it too much, because empirically, when they do it too much, things work not good. But of course, you see that what I'm doing here cannot be applied directly to reuse, because if you do reuse, these things are not independent. So now we come into a different part of mathematics. You know what happens with one trial, right? And you redo it, but you redo the same noise, in fact, by reusing. But what they do, they don't use the same noise really. What they do normally, that's a cool problem, if somebody wants a cool problem, is that they take their data set and they randomly, they use a random permutation, right? So that it's like random, right? You had a large number of things, you just randomly permute them, and now do this. Now it's become a cool problem. You have a function of a random permutation, you have a sequence of random permutation, it becomes a cool problem on the random permutations, which I haven't tried, if somebody wants to try. But reuse is in fact used seriously. So at some point somebody must understand. I'm tired of this, so I will just not study reuse right away, but so it's completely open if you want to.
Okay, I think we should stop here, but of course there are ask questions during the break, so we'll have 15-minute break, and thank you very much.